Hello everyone and welcome to CSEN701 Embedded Systems Architecture, also referred to as Real-Time Embedded Systems. My name is Walid Al-Hifni and I'll be your TA for this course alongside Loa Zahar. First of all, welcome to the new semester. I hope you guys enjoyed your summer vacation regardless of the COVID-19 pandemic. Today we're going to discuss tutorial 1, which tackles real-time systems and real-time embedded systems. But before we start, let me show you the course outline. As you can see, we have 40% for the final, 25% for the midterm, 10% for the quizzes, best n-1 out of n, and finally 25% for the project. The project will be similar to your digital system design or DSD course, where you will deal with electrical components, but instead of using the FPGA board, you will be using an Arduino board. And in the upcoming tutorials, we will tackle how to use the Arduino board. We also created a Piazza course page for the embedded systems course, where you can ask questions regarding the course logistics, the quizzes, the content of the lectures and tutorials. So if you have any question, just post it on Piazza and one of the course instructors, me, Loa, or Dr. Hassan will reply to you. So as you can see, we will be implementing the hybrid teaching methodology. In the tutorials, we have a total of 10 practice assignments, 4 theoretical assignments and 6 practical assignments. However, we'll be giving 5 tutorials or 5 practice assignments out of the 10 on campus. So all tutorial groups will take the same exact 5 practice assignments. And there will be 5 practice assignments exclusively online that they will not be given in the tutorials. We will be giving all 4 theoretical assignments plus 1 practical assignment on campus to all groups. However, the rest of the practical assignments, the other 5, will be given exclusively online, and you guys need to watch the videos because you will be asked in your exams, whether the quizzes, the finals, or the midterm, about the content of the practical assignments. So it's really important to actually watch the practical assignments that will be given online and also attend the theoretical assignments on campus. However, all 10 tutorials or all 10 practice assignments will be available online as videos. But as I told you, we'll be focusing on 5 out of the 10, and these 5 will be given to all students, to all tutorial groups on campus, and the other 5 will be given exclusively online. Now let's start with the content of our tutorial and let's talk about real-time systems and real-time embedded systems. So in the first part of the tutorial, we'll be tackling some important definitions regarding real-time systems and real-time embedded systems. You need to know them by heart, but do not memorize them. Okay, you can express these definitions in your own words. There are some keywords that must be present in your solution. However, you can express these keywords using your own words. And let's start with the first definition and let's define what is a real-time system. A real-time system is any information processing system which has to respond to externally generated input stimuli within a finite and specified period. So actually, a real-time system is any information processing system. And information processing systems are like our PCs, are like our computers, okay? They process information, they process data, which has to respond to externally generated input stimuli. So actually, a real-time system must provide a response to a certain input, okay? And this input is externally generated. So there is an input entering our real-time system, and a real-time system must actually respond and send a reply or a response to this according to this input. However, there is a constraint, which is the time constraint. Therefore, we have within a finite and specified period. And this is very important because real-time systems have to meet their deadlines. Okay, they need to actually respond in a specific amount of time. They should not miss any deadline, or they should not miss their deadlines. So our keywords here are information processing system and to respond to externally generated input stimuli, meaning that it responds to an input. And the third keyword is within a finite and specified period of time. So you can express these 3 keywords, the information processing system responding to an input stimuli and within a specific or a finite amount of time. You can express these keywords in your own words. Let's move on to the second definition and let's define what is a real-time embedded system. So real-time systems are called RT systems or RTS. A real-time embedded system is called RTES, and you will be seeing RTES in the lecture slides, in the tutorials, and in your exams frequently. So you need to understand that RTES stands for real-time RT and ES stands for embedded systems. So real-time embedded systems. An embedded system is a computer system that is part of a larger system. It interacts with the environment or with its environment, usually with real-time computing constraints. So what is an embedded system? Embedded system is a small computer system that actually is part of a larger system. So a large system contains multiple embedded systems, and hence comes the word embedded because it's small and it actually contributes to the larger system. So it's part of a larger system. For example, we have a car. A car contains multiple embedded systems. All of these embedded systems form the car system, the overall large car system. Okay, it interacts with its environment. So actually, as we all know, interacting with the environment, meaning it actually takes input from sensors and gives back or responds by outputting some data using actuators. So as you know, sensors for inputting data and actuators for outputting data. So a real-time embedded system or an embedded system actually interacts with its environment, usually using sensors for input and actuators for output, usually with real-time computing constraints. And this sentence makes the difference or highlights the difference between real-time embedded systems and non-real-time embedded systems. So since we are defining real-time embedded systems, we now have a deadline that we need to meet, okay? We need to respond in real time. We have a timing constraint. Therefore, with real-time computing constraints must be present in the definition of real-time embedded system. So the keywords here, that an embedded system is a computer system that is part of a larger system. So it's a small system part of a larger system. The second keyword, that it interacts with its environment. And the third keyword, since it's a real-time system, we need to actually specify the real-time constraints, the timing constraints. Let's move on to the third part or the third question. Could an embedded system not be a real-time one? Non-real-time embedded systems are not time-bounded. So as I told you before, we can have real-time embedded systems and non-real-time embedded systems. And the difference is regarding the timing constraints. So actually, non-real-time embedded systems exist. However, they are not bounded by any time constraints. So let's move on to our next question. And what would be the characteristics of such systems? Meaning, what are the characteristics of embedded systems? They keep the embedded characteristics as follows. The first thing is little or no user intervention. So actually in embedded systems, users should not actually directly intervene or interfere with embedded systems. They are performing their tasks automatically without any user intervention. There is no user interface for the user to interact with the system. The system has a program installed on it, or the embedded system has a program installed on it, and it is performing its task without any user intervention. The second item, small memory. Embedded systems actually have small memories in terms of kilobytes, not like our PCs or laptops in terms of gigabytes, because the embedded system is a small system. Therefore, we do not have any space to add larger memories. Hence, the memories of the embedded systems are small. So the second thing was that they have small memories in terms of kilobytes. The third thing is that limited number of peripherals. So in an embedded system, it is not connected to multiple input and output sources. Not like your laptop, for example, or your desktop PC. You can connect it to a screen, keyboard, mouse, speakers, USB, memory stick. You can connect it with an HDMI cable or an external hard disk. An embedded system is actually having a limited number of peripherals. And as you will see in your project, using the Arduino board and the microcontroller on the Arduino board, you'll find out that you do not have a lot of space or a lot of peripherals to connect input and output items. Therefore, there are limited number of peripherals and it varies according to the embedded system. So some embedded systems have a limited or a small number others have a slightly higher number. And you will see this when you implement your project and find out that there are different Arduino boards. And the main difference is that, for example, the Arduino Mega board contains more input-output pins compared to the Arduino Uno board, for example. But however, the general rule of thumb is that it has a limited number of peripherals. Finally, embedded systems have a limited number of tasks, meaning that an embedded system is not a general purpose computer. It's not like your PC or laptop. It has a certain specific task and it will be doing it automatically. Okay, it may have multiple smaller tasks or multiple small tasks. However, it has a limited number of tasks. It's not like any general purpose computer that can actually implement thousands or millions of tasks. No, it is limited. It has one or two or even three tasks that can perform, or even more, but I mean, they are not huge like compared to your PCs and desktops. So to summarize it, the embedded characteristics are as follows: little or no user intervention. The user is not interfering with the embedded system, except for uploading the program at the beginning. So actually, when you manufacture an embedded system, you will flash a program on it, and then you will implement it in the car, in the electrical washing machine, whatever. However, you as a user, you do not actually reprogram the embedded systems in your car or in your washing machine or microwave. They are actually built in and programmed by the manufacturer, and you are just using them without any interference. Small memories, embedded systems have small memories in terms of kilobytes, because due to the size and space, we have limited number of peripherals. We do not have the luxury to actually connect to multiple input and output sources because they are small. So we have limited number of pins to connect to. And mainly, actually, embedded systems, one of its main roles are to interact with each other to perform complicated tasks. So actually, if you want to perform a complicated task in your car, the multiple embedded systems present in your car will communicate together to perform such task. And for example, if an embedded system wants an input and it is not directly connected to the sensor, it will request the data from another embedded system that is directly connected with the sensor. Finally, limited number of tasks. Embedded systems are actually have small memories, so they have we cannot actually flash huge programs. Therefore, they are having a limited number of tasks, small tasks, not general purpose tasks like your computers and PCs. Now, imagine an example of a non-real-time embedded system or a non-RTES. Actually, as I told you before, we can have non-real-time embedded systems. But actually, where can we find non-real-time embedded systems? Let's imagine this scenario. Imagine a weather station places somewhere where human presence is less accessible. So actually, you have a weather station that is placed somewhere where humans cannot easily access this station. For example, like the desert or rural areas where actually you cannot be physically present all of the times. This system is built just for one single thing: reading information from several sensors and transmitting them via a network link to a base station, meaning a desktop PC. So basically, this weather station is built to read information from its environment. That's why it's an embedded system, because it is interacting with its environment. So the sensors will actually input data to this system, and using a network, this data will be transferred to a desktop PC, for example, in a city or in the headquarters of the weather station channel, for example. This embedded system is required to provide information just several times in a day, so it does not have to continuously monitor its inputs and to provide outputs on a fixed pre-established time frame. So actually, a real-time embedded system means it must listen to its environment 24/7. Okay, a real-time embedded systems must be always on, always monitoring the environment. Once a change occurs, it must respond immediately, because we have a deadline or a time frame, a specific time frame. However, in the case of our weather station, I do not need to have the sensor read 24/7 the data. So we can actually read the data, for example, 3 times a day and then transmit it to a network. Therefore, this embedded system will wake up, for example, every 5 or 6 hours, will read the data using the sensors, and then will transmit it to the desktop PC or to the weather station headquarters in the city. and then it will sleep again. So actually, if something occurs in the environment around the weather station, will the sensors be actually listening to it while it's sleeping? No. Therefore, it is a non-real-time embedded system, because even if a change in the environment occurs, but the system will be sleeping because it only reads the data across several time periods, not continuously. And it is very important that real-time systems are continuously reading and monitoring the environment. Now we are done with the first part of the tutorial, which was some important definitions. Let's move on to the second part of the tutorial and let's discuss the types of real-time systems. We'll just go briefly in the tutorial. We'll not discuss it as much as stated in the lecture. So we have three main categories. We have soft real-time systems, we have firm real-time systems, and we have hard real-time systems, and a subset called the weakly hard real-time systems. The difference is as follows. Soft real-time systems are actually systems that need to meet their deadline. However, if they did not meet the systems that need to meet their deadline. However, if they did not meet their deadline, no catastrophe will occur. For example, like if you're watching Netflix or YouTube, there are some delays. These delays will actually not result in a catastrophe. You will not die from these delays. Yes, you will be bothered that, for example, YouTube is buffering. YouTube is not meeting its deadlines. However, at the end of the day, you are well, nothing occurred to you, you're just frustrated, but you will continue the video when the buffer ends. Same goes, for example, to the ATM machines. When you click on a button on the ATM machine, it may actually take time to load. For example, if you want to withdraw 200 pounds and you click on 200, it will take some time to actually give you the money. However, at the end of the day, you will take your money, but you will not take it in the same instance you clicked on 200 pounds. These are the soft real-time systems. The second category is the firm real-time systems, meaning that the computation will be obsolete. So if it misses a deadline and then gives you the computation afterwards, you will not need this computation anymore. And the famous example is Google Maps. If you're actually navigating and there is either you go left or stay forward. So you should actually, or the GPS should have notified you that you need to turn left. However, it provided you with this information later after you continued forward. So actually it provided you with the information. However, it provided you with the information after you missed the left turn. So you got your computation, but the computation is obsolete. Now it does not mean anything. You will not need this computation any longer. Same goes for the weather example the doctor described in the lecture, which is if you're traveling and it told you that the city you're going to or your destination city is sunny. However, when you arrived, you found it raining. Okay, well, yes, it notified you when you arrived that take care, it's raining. But however, at the beginning, it told you that it was sunny. So it did not compute or did not inform you earlier that you need to take precautions that it will rain. Therefore, when it informed you that it is raining, it was too late because you arrived to your city and you find out that it was raining. So yes, it provided you with the information that, guess what, it's raining. However, it provided you after, or the data arrived to you late. Okay, therefore, it is useless for you. You will not do anything with this data. The third type is hard real-time systems. And actually, hard real-time systems, if they miss the deadline, a catastrophe will occur and you may die, for example. And there is a subset called the weakly hard real-time systems. The weakly hard real-time systems implement redundancies just to make sure that you will not die. So actually, if you have the luxury or you have the possibility to implement redundancies for a system to meet its deadline, then it will be a weakly hard real-time system. An example is, for example, the car brakes. Okay, a car brakes originally is a hard real-time system because if you brake and it does not stop, you will die. However, in modern cars, there is a redundancy in the braking systems. So actually, instead of having one deadline to meet, which is if you did not meet, you will die, we implement redundancy. So you'll have, for example, a full braking system that consists of 3 deadlines. And you need to at least meet 2 out of the 3, or for example, 1 out of the 3 for the car to brake. So this transformed the car brakes from hard real-time systems that you need to meet all of your deadlines to a weekly hard real-time system that meeting one or multiple deadlines out of the total deadlines will make you safe and will keep you safe. Hard real-time systems, as the doctor stated, the pacemaker, which actually regulates the heartbeats, is a hard real-time system, and it does not have any redundancies due to its small size. Therefore, it cannot be a weakly hard, because actually if it misses a pulse or two, the person may die. However, for weakly hard real-time systems, for example, the airplane systems, the car systems, and the train systems, they actually implement redundancies. So actually, for example, if you want to brake and you pressed on the brakes, there are, for example, 3 deadlines that you need, or 3 total deadlines, you need to meet at least one of them for the car to stop. So meeting one out of the 3 deadlines will allow the car to stop. However, if you did not meet one out of the 3, you will die. And that's why it is classified as a weakly hard real-time system, because that's even if I meet one out of the 3 deadlines, I will be safe. However, if I did not meet at least one out of the 3 deadlines, I will die, or a catastrophe will occur. Therefore, it is a weakly hard real-time system. Let's move on to our question. Question 2. What do we call a system in which the distribution of its met and missed deadlines during a window of time is precisely bounded? What does this mean? It means that we have deadlines, we have a total number of deadlines, and there is actually a distribution regarding meeting some deadlines and missing some deadlines. So what type of the 4 systems, soft, firm, hard, and weakly hard, does it actually have at least a minimum number of deadlines that needs to be met? As you all figured out, it is weakly hard real-time systems, because there is a distribution between meeting some deadlines and missing some deadlines. As the braking example, if you meet one out of the 3 deadlines, meaning you missed 2, the car will stop. That's why we have a distribution. You can actually say, yes, I can meet X deadlines out of Y deadlines, and I will be safe. This is weakly hard real-time systems. Can the effect of missed deadlines be different depending on whether these deadlines are missed consecutively or non-consecutively? And explain using illustrative examples. So actually want to see whether if I have, for example, a weakly hard real-time system, and I need to meet, for example, 4 out of the 10 deadlines. Will it differ if I meet the 4 consecutively or non-consecutively? And actually missing consecutively or non-consecutively, let's see. Yes, of course. For instance, in a computer-controlled system, missed deadlines result in loss of control performance. This performance loss depends on the total number of missed deadlines over a period of time. On the other hand, in digital audio systems, the quality of the output produced is more sensitive to the number of consecutive missed deadlines. If the same number of missed deadlines occur non-consecutively, its effects may not be noticeable. What does this mean? So as you can see, there is a difference between missing deadlines consecutively and non-consecutively, and this will affect some types of systems. For example, a computer-controlled systems does not depend on the consecutive missing of deadlines, meaning that when you miss deadlines, you will lose performance. However, some computer-controlled systems, they care about the total number of missed deadlines, whether they are consecutive or non-consecutive. However, the total number is the main factor for these computer-controlled systems. However, there are some other types of systems, for example, audio and video systems, where actually losing or missing deadlines consecutively will result in a major issues. Okay, just imagine that missing a deadline is like dropping a packet. A packet is not received to you. So if I'm streaming an audio or a video and the packets are dropped non-consecutively, this is good because yes, I will feel some delay or lag, but the video feed or the audio feed is still running. However, if I start to miss deadlines or drop packets consecutively, I may reach a level that I cannot see or hear anything because consecutive packets are being dropped, are not being received. I'm not meeting the deadlines consecutively. I'm missing a lot of consecutive deadlines, and this will affect the output produced, whether it's an audio or a video application. Therefore, we need to actually classify weakly hard real-time systems into consecutive missing of deadlines and non-consecutive missing of deadlines. As I told you, some systems does not matter, like the computer control systems. At the end of the day, I care about the total number of missed deadlines. I do not care about the consecutiveness of these deadlines. However, in applications like digital audio and digital video systems, missing the deadlines consecutively will result in major issues that we need to take into consideration. Therefore, we can classify weakly hard real-time systems into consecutive and non-consecutive regarding the deadlines. And here comes a question regarding the constraint of weakly hard real-time systems. Okay, so this is some description. It states that for symmetry purposes, it is also interesting to be able to specify the number of met deadlines as opposed to the number of missed deadlines. So actually, in the previous question, we were tackling whether we are missing or deadlines consecutively or non-consecutively. However, here we want to actually specify the number of met deadlines compared to the number of missed deadlines. For instance, in a certain control system, after a deadline is missed, it may be necessary to meet at least 3 deadlines in a row so that the state of a system is correctly updated. So let's just have this example. If I have a system, and actually if I miss one deadline, in order for the system to actually work again properly and correctly, it needs to meet 3 deadlines. Okay, in a row, which means 3 consecutive deadlines. So actually, if I miss one deadline, I need to meet 3 consecutive deadlines in order for the system to be functioning properly again. And that's a constraint that may be actually in a control system as stated by the question. This introduces a further classification of those systems. To ease the notation, the tolerance to missed deadlines is established within a window of m consecutive invocations. So actually here we will be saying that m is the total number of consecutive invocations, okay, which also corresponds to a window of w equal t multiplied by m units of time, where t is the period of the system. So actually, if I want to actually know the time, because actually if I say m consecutive invocations, it means I invoked 3 times, 4 times, 5 times. However, if I want to know the exact time or the period it took, I need to multiply the period of one invocation multiplied by the total number of invocations. Therefore, this will specify the time. The combination of the two considerations, now we have 2 different classifications, whether consecutiveness versus non-consecutiveness, which we described in the previous question, or here we have missed versus met deadlines. As I told you, for example, if you miss one deadline, you need to actually meet 3 deadlines in a row for the system to be working properly. And this is example. Leads us to 4 types of constraints. So actually, we have 2 categories, consecutiveness versus non-consecutiveness, missed versus met. How many total number of combinations? 4. Missed consecutiveness, or missed consecutive, missed non-consecutive, met consecutive, met non-consecutive. So we have 2 categories, which results in a total of 4 combinations. It's so simple, simple math. Missed consecutiveness, missed non-consecutiveness, met consecutiveness, and met non-consecutiveness. And an example was provided in the question. So one of the 4 constraints was already provided for you in the question. And this is the provided constraint. A system meets any n in m deadlines if in any window of m consecutive invocations of the system, there are at least n invocations in any order that meet the deadline. So actually, we are here tackling meeting the deadlines, not missing. Remember the second category, misses versus met. Here, this example from the beginning states that a system meets. Okay, so we are in the meet category. So here it says that a system meets any n in m deadlines. So I have a total of m deadlines. And how can I say that I met n out of m deadlines? If in any window of m consecutive invocations of the system, there are at least n invocations in any order. And when we say in any order, do we mean consecutiveness or non-consecutiveness? As you all guessed correctly, we here mean non-consecutiveness, because in any order means it is not consecutive that meet the deadline. So actually, we are here in the meeting category. We want to know How can a system meet n in m deadlines? So for a system to meet n in m deadlines, there must be at least n invocations in any order that meet the deadline. So if I have m deadlines, in order to meet n deadlines, what shall I do? I need to at least meet n in any order. This order may be consecutive, non-consecutive, I don't care. At the end of the day, I must meet n invocations out of m for a system to be said that it meets any n in m deadlines. I know it is somehow complex, but actually in the physical tutorials, and by the way, this tutorial will be given physically to all groups on campus. So watching the video will make you remember what was being said in the tutorial. But it's really important to actually understand this example. We are trying to here meet how to say that a system meets any n in m deadlines. How can I meet n in m deadlines? If actually in m consecutive invocations, there are at least n deadlines that are met in any order. Therefore, I can say that this system met n in m deadlines. If you want to actually deduce the three other constraints, we will also be tackling the other direction, which is meet or met consecutive, because the first one tackled met non-consecutive when we stated in any order. However, here we will be tackling met consecutively. So a system meets row n in m deadlines. And take care, above we stated what? A system meets any n in m deadline. N means it may be consecutive, it may be non-consecutive, I don't care. However, in the second constraint, a system meets row n in m deadlines. How can I actually say that the system met n consecutive deadlines out of m? If in any window of m consecutive invocations of the system, there are at least n consecutive invocations that meets the deadline. So I can say that a system met n in m deadlines consecutively if I have m consecutive invocations and the system at least meets n invocations in a row, or meets n consecutive invocations in a row. So as you can see, the second constraint tackles meeting consecutively, while the first constraint met what, or tackled what? Met non-consecutive. So from here we can deduce the keyword that a system meets any. Meets means what? That I'm in the met, not the missed category. And any n in m deadlines refers to non-consecutiveness. Therefore, this constraint was tackling the non-consecutiveness of meeting deadlines. There are at least n invocations in any order, and in any order also refers to non-consecutive. In the second constraint, a system meets row n in m deadlines. Row means it is consecutiveness, and or it is consecutive. And a system meets, here we are tackling the meets, not the misses. Therefore, meets row means it is meeting consecutively. How can I say that a system is meeting consecutively or n and m deadlines in a row? There are at least n consecutive invocations that meet the deadline. So if I have m invocations, I must have at least n consecutive invocations so that I can say that this system has met row n and m deadlines. Now we have the other two constraints, which will be tackling the misses. So as you can see here, a system misses, and we here are tackling the misses or the missed deadlines. So a system misses what? We can have miss consecutive and miss non-consecutive. From this example, a system misses any n and m deadlines. Any here refers to what? To non-consecutiveness. So therefore, this is the combination of miss non-consecutiveness. A system misses any n and m deadlines if in any window of m consecutive invocations of the system, no more than m deadlines are missed. And take care, we are here tackling the misses and not the meets. So actually, to say that a system has missed n and m deadlines in any order means that what? No more than m deadlines are missed in any order. No more, not at least. Okay, no more, because missing n deadlines, this is the maximum number of deadlines that I can miss. Take care, it's really important. Missing n deadlines means this is the maximum number that the system can tolerate. Therefore, no more than n deadlines in any order can be missed. Moving on to the fourth constraint, a system misses row n and m deadlines if in any window of m consecutive invocations of the system, it is never the case that more than n consecutive invocations miss their deadline. So actually we are still in the misses category or the missed category. However, if the previous constraint was tackling misses non-consecutive, this constraint will tackle misses consecutive. Therefore, it is stated that a system misses row, and row indicates the consecutiveness factor. A system misses row n in m deadlines if in any window of m consecutive invocations of the system, and as you all saw, this phrase, if in any window of m consecutive invocations of the system, is present in all four constraints. It is never the case, okay, so actually we are denying, it is never the case that more than n consecutive invocations miss their deadline. So actually, in order to say that a system misses consecutive n and m deadlines, it would be impossible for the system to miss more than what? More than n consecutive deadlines. Okay, that's why it said it is never the case that more than n consecutive invocations miss their deadlines. Because in order to say that a system misses row n and m, the system should not actually, by any means, miss more than n consecutive invocations in a row, or n consecutive invocations. Okay, so as a summary, as you can see here, we are tackling two types of categories or categories. We have consecutiveness versus non-consecutiveness, and meeting versus missing, or missing versus meeting. And we had four different combinations. How can I say that a system actually meets any n and m deadlines, meets row n and m deadlines, misses any n and m deadlines, and misses row n and m deadlines? So all four combinations were presented, and the question provided you with the first constraint, and you had to actually deduce the rest of the three constraints. Let's move on to our last question, which is a case study regarding a cell phone. Okay, so it's a mobile phone case study. Figure 1 shows the components of a radio, which is the heart of a cell phone. So at the bottom of the screen, we have here figure 1. We have here an antenna, an RF amplifier, a mixer, a filter, a demodulator, and a decoder. I guess the DMT guys will be familiar with such stuff. The radio signals are first received by the antenna, amplified, and passed through a mixer, then filtered, demodulated, and finally decoded. And by the way, this is describing how to receive a radio signal, because it is first received by the antenna, then it will be passed by the RF amplifier to be amplified, then it will be passed through a mixer, then filtered, then demodulated, and finally it will be decoded. Okay, the antenna acts as the interface between the medium through which radio waves travel and the electronics of the transmitter or receiver. So actually the antenna tries to listen to or receive the signal that is actually passed through air or the atmosphere. Antennas can be designed to work best in particular directions, giving both transmission and reception directional or direction properties, meaning that we described the case of receiving a signal. However, antennas can actually transmit signals, for example, to radio towers or to other cell phones. So the antenna is working bidirectional. It can receive and it can transmit. And modulation encodes information in the amplitude, phase, or frequency of the signal to increase its robustness under impaired conditions. So actually modulation tries to enhance the signal and makes it actually robust, so you can receive it well without, or you receive it actually accurately without any problems or issues. Okay, so basically modulation is just to enhance the signal. You should not actually know these components or terminologies. This is a case study, and you will be provided in the exam, for example, with case studies, and the case studies will be self-describing. Okay, so we will actually provide you with a description that tells you what are the components present in the case study that will be in your exams. So you should not know actually what is the role of the antenna, the modulator, etc. Okay, you will just have all the information provided in your exam, and you will try to deduce the answers to most of the questions. Okay, let's move on to our first question. How do radio transmitters work? So actually we described how do we receive signals. Here the question asks how do we transmit signals. So let's take the diagram, which is figure 1, Instead of moving from left to right, we want to move from right to left. So instead of a decoder, it will be what? An encoder. Instead of a demodulator, it will be what? A modulator. Then a filter, a mixer, an amplifier, and antenna. Therefore, the answer is the radio transmitters go through the same steps, just in the opposite order, which I just described. I mean, now I described the opposite order of starting from an encoder instead of a decoder, a modulator instead of a demodulator, then filter, mixer, and RF amplifier, and then it is sent to the antenna to transmit it. Originally, all components were analog, but over time, most were replaced by digital components, requiring the radio signal to be converted from analog to digital. So back in the old days, everything was somehow analog. However, with the new technologies, we are transferring analog signals to digital signals, or we are moving into digitalizing the components. The desire for flexibility in the number of radio bands led to software routines replacing some of these functions in programmable chips, such as digital signal processors. Because such processors are typically found in mobile devices, emphasis is placed on performance per joule, performance per square millimeter of silicon, and bytes per task. So actually, we are starting to use programmable chips containing digital signal processors to actually process the digital signal instead of the analog signal, because we are moving towards digitalizing most of our components. And since we are using actually processors that are found in mobile phones, and take care, mobile phones are small devices, they are not large devices. Therefore, there are some constraints like the performance per joule, performance per square millimeter of silicon, and bytes per task. So why do we emphasize in DSPs and in real-time embedded systems in general on performance per joule, performance per square millimeter of silicon, and bytes per task? All right, so let's take each one alone. The emphasis is placed on performance per joule to extend the battery life. So actually, as you all know, joule represents the unit of energy. Okay, so performance per joule will definitely affect the battery life. And we actually care about the battery life of what? Of our mobile phones. As you all know, you have mobile devices, and one of the main issues of your mobile devices will be the battery. Okay, so actually we need to take into consideration performance per joule to lower the battery to lower the battery consumption, therefore to extend the battery life. So per joule refers to energy. And what is the component present in our mobile phone that consumes energy? The battery. It's the source of energy in our mobile phone. Therefore, performance per joule reflects the battery life. The second item is performance per square millimeter of silicon. And this is to reduce the size and the cost. Because silicons are very expensive, and therefore we need to take into consideration the size of our chip, and therefore performance per square millimeter. Now we are talking about square millimeter. This is what? This is size. It's a measurement unit for size. Therefore, we want to reduce the size and the cost. So it's self-explanatory. I mean, in the previous one, per joule, it's energy, so it's battery life. Here, per square millimeter, so it's size. So you want to reduce the size, and actually reducing the size will reduce the cost, because if the size is bigger, you will actually spend a lot. Finally, bytes per task. So actually here we are saying bytes. Bytes is a unit of what? It is referring to the memory. Therefore, bytes per task to reduce the memory size. Okay, because if I actually focus on making our computation use less memory and the data is actually smaller, therefore we can store it. Therefore, we will reduce the memory size, which will also reduce the cost. Therefore, performance per joule is to extend the battery life. Performance per square millimeter of silicon to reduce the size and the cost. And finally, bytes per task. And as I told you, bytes refer to what? To memories. Therefore, we want to reduce the memory size. Okay? Now, let's move on to the next question. And figure 2 shows the generic block diagram of the electronics of a cell phone handset. So as you can see here, we have an antenna and an RF receiver and an RF transmitter. And then we have the digital signal processing unit, where it actually processes any signals. And we have the microcontroller unit. And as you can see, the DSP unit is actually connected to the speaker and the microphone, because these devices need signal processing. I mean, if I'm using the microphone and I'm talking, I need to actually process the signal that is an input signal, and vice versa. If I'm receiving a signal and I want to output to the speaker, I need to actually process this signal and output it to the speaker. So actually any processing, any signal processing must be performed inside the digital signal processing unit. However, any type or any other type of processing is done through the normal microcontroller. As you can see here, it is connected to a display and a keyboard. So how many processors are there in figure 2? Why and what other modules exist in a cell phone? As you can see from figure 2, we have two main processors. Okay, we have the digital signal processing unit, which actually processes, from its name, it processes signals, and we have the microcontroller, which actually contains a small processor for the other purpose tasks. Therefore, we have two processors. The DSP performs the signal processing steps of figure 1. If you remember figure 1, we can go back actually to figure 1. Here, all of these steps are actually done inside the DSP. So apart from the antenna, the RF amplification, the mixer, the filter, the demodulator, and the decoder are all happening inside the DSP, and vice versa if I'm starting to transmit, not to receive. So I'll be having an encoder, a modulator, filter, mixer, and RF amplifier. So we go back, and the microcontroller actually controls user interface, the battery management system, the call setup, and the rest of the tasks. So actually all other tasks that does not need any signal processing are done through the microcontroller. However, signal processing tasks are done inside the DSP. Actually, what are the other modules that exist? The cell phone handsets are basically mobile computers acting as a radio. So your smartphone or mobile phone is a computer device, a small computer device. However, it is trying to act as a radio because you actually transmit calls and receive calls. They include standard I/O devices, typically because they are small computers. So you can find keyboards and LCD displays in old-fashioned mobile devices. New mobile devices actually are touch screens. So the display is actually touch, not just an LCD display with a keyboard. Plus, definitely we have a microphone for the input of the voice or the voice input. We have a speaker to output the call or the voice. And finally, an antenna for wireless networking. So these are the other modules that exist in a cell phone. One of the important aspects is the battery management or the battery efficiency, because the battery efficiency affects sales both for standby power when waiting for a call and for minutes of speaking. And as you can all see, when you actually perform a phone call with your friends, when you stay longer during the call, you will find out that your battery reduces. So actually, yes, because it needs a lot of power, a lot of energy to transmit and receive and then process the signal. So a lot of operations are occurring, therefore the battery efficiency will be reduced and actually use more power. Therefore, the battery reduces. Therefore, actually, it's really important, and most of you have seen it. When you spend a lot of time on the phone, you find out that your battery percentage has decreased with a huge factor. This is mainly because we perform a lot of signal processing operations trying to actually the receiving signal and the transmitted signal. Finally, this is our final question in this tutorial. When a cell phone is turned on, the first task is to find a cell. Okay, and a cell is like a tower. It scans the full bandwidth to find the strongest signal, which it keeps doing every 7 seconds, or if the signal strength drops, since it is designed to work from moving vehicles. So actually, when you power on your cell phone, it will try to connect to the nearest tower. And here we say cell instead of tower. It then picks an unused radio channel. So actually, when it connects to your tower or to the cell, it will use or it will try to find an unused radio channel, and this will be dedicated for your communications, exclusively for you. The local switching office registers the cell phone and records its phone number and the electronic serial number and assigns it a voice channel for the phone conversation. So once you find an unused radio channel, the local switching office will start to record your phone number and your unique IDs. Each mobile phone has a unique ID. Each SIM card has a unique ID. All of this data will be recorded, and you'll be given a voice channel to perform your phone conversations. To be sure that the cell phone got the right channel, the base station sends a special tone on it, which the cell phone sends back to acknowledge it. Same as networks, okay? So actually, to make sure that the phone uh, received the correct channel, the base station or the tower will send a request. It's like an acknowledgement, okay? It will send a request and it will wait for the cell phone to send a response, which is the acknowledgement. So to make sure that actually the connection is set up and you are on the correct channel. The cell phone times out after 5 seconds if it does not hear the supervisory tone and it starts the process all over again. So actually, if the cell phone does not get a feedback from the tower, what is the channel that I'm going to use after 5 seconds, it will actually cut all communications and will start from the beginning. So actually the supervisory tone is the tone, the special tone sent by the base station to make sure that you receive the correct channel and then you acknowledge as a cell phone this special tone. However, if you did not receive this special tone after 5 seconds, the cell phone will try to recreate the process from the beginning, okay, checking for an unused radio channel, etc. The original base station makes a handoff request to the incoming base station as the signal strength drops off. So actually, if you are moving from an area to a different area and the different area has its cell tower, so actually the original or the previous cell tower will alert the new cell tower with the information so you can continue your conversation. Okay, because actually if it does not do a handshake, the phone call will be failed. And actually this is one of the main reasons why most of the phone calls, or when you actually a message appears and for example it tells you call failed. Why it is failed? Because actually you are moving from one area to another, so you will be switching towers. So this switching towers may actually drop the signal and therefore you need to create it from the beginning. Therefore the towers actually try to acknowledge or inform the next tower when you are leaving its area. To achieve a two-way conversation over radio, frequency bands are set aside for each direction, forming a frequency pair or channel. The original cellular base stations transmitted at 869.04 to 893.97 MHz, called the forward pass, and cell phones transmitted to or at 824.04 to 848.97 MHz, called the reverse pass, with the frequency gap to keep them from interfering with each other. So actually this describes that the cell phone and the cell tower actually operate at different frequencies. Okay, the cell phone will the cell tower will transmit at a range, and the cell phone will transmit at a different range, and there is a gap in between to prevent any interference. Because if we do not have any gap, we can have actually the cell phone and the cell tower will interfere with each other. Therefore, the cell tower will operate at certain frequencies, the cell phone will send at certain frequencies, and there is a gap in between to prevent any interference. Okay, and it's really important because each direction operates what on a different frequency range. The cell tower has its own frequency range for transmitting, and actually the cell phone has its own frequency ranges for transmitting. So as you can see, these ranges are for the transmission, meaning that I'm a base or a cell base station, I'll be transmitting at my specific range. Therefore, the mobile phone or the cell phone must actually receive in this particular range. However, the cell phone transmits at a totally different range. Therefore, the cell base station must receive in this particular range that the cell phone is transmitting to. Okay, and there is a gap in between to prevent any interference. Cells might have had between 4 and 8 channels, and channels were actually divided into setup channels to actually set up your call, and voice channels to handle the data or the voice traffics. So actually have multiple channels, and the channels are divided for either having call setup channels to set up your call at the beginning, or actually voice channels to handle the voice traffic. The communication is done digitally, just like a modem, at 9600 bits per second. So actually 9600 bits are transmitted per second, and it's a digital communication. It is not an analog. As I told you before, we are moving into digitalizing everything. So the signals are actually digital signals, and since they are digital, they are bits, zeros and ones. And it is done through a rate of 9600 bits per second. The handset sends each message 5 times. So actually, every time I send a message, I will send it 5 times, okay? The original cell phones typically transmit at 2 signal strands, either 0.6 watt or 3 watt. And now let's have our questions. Why does the handset send each message 5 times? So why actually do I bother sending the same exact message 5 times? As you all figured it out, 5x means wireless is a lossy medium, especially from a moving vehicle, because actually we are transmitting through air, and air is a lossy medium, especially if you are driving a car. Okay, so the probability that you will drop packets in the middle is high. Therefore, to make sure that the packet is received to the cell tower from your handset or cell phone to the cell tower, you need to transmit it 5 times to make sure that it arrives correctly without any errors and is not lost, because wireless is a lossy medium. The second question is, why 2 signal powers for transmission? Why can I transmit at 0.6 watt or at 3 watt? What is the difference? To preserve battery life depending on the distance to the cell or to the tower. So if I'm actually near the tower, I do not need to transmit at 3 watts. I will just transmit at 0.6 watts, which will actually preserve my battery life. Because as I told you, if you use a higher energy for transmission, the battery life will be reduced. Therefore, if you are near the tower, why should I actually use a higher signal strength? Okay, I'm near the tower, so I should actually use a lower signal strength. Therefore, it is not just one unified strength regardless of the distance. No, according to the distance, and the distance is a very important factor. If I'm close to the tower, I'm going to send using 0.6 watt. If I am far from the tower, I'm going to send using 3 watt. Now I'm done. I hope you guys enjoyed the tutorial. As I told you before, this tutorial will be given on campus to all students. So this must be, or this tutorial is just like a revision for the actually given tutorial on campus. If you have any questions, this is our course email, but you can use Piazza to actually post your questions and use or keep using our emails to a minimum. Okay, because it's better to actually post your question on Piazza, and all of the students will actually can see your question and see our reply. So good luck, and we'll see you inshallah in the next tutorial. The tutorials will be divided between me and Loa. So actually I will be recording the theoretical tutorials for now. Loa will be recording the practical tutorials. So I will see you in tutorial 3, and stay safe, stay home, and good luck.